We've examined how Newton's first and third laws can apply to force diagrams to help explain how and why objects move. Newton's second law deals with acceleration, so now we're looking at unbalanced forces. Even though these forces that cause acceleration are unbalanced, there may be balanced aspects. For example, horizontally you may be accelerating, but vertically you may be balanced. Understanding these balanced forces and how to write balanced force equations will help us infer unknown forces from known or calculated forces. Writing balanced force equations is a four-step process. 1. Always start with a force diagram of the motion. Every time you're talking about forces, a force diagram is a great starting place. Step 2. We need to ask ourselves, are these forces balanced or unbalanced? Look at the forces horizontally or the forces vertically. Up balances down, left balances right. Once you've determined what's balanced and what's unbalanced based on the magnitudes of the forces you've drawn, write out the forces that are equal to one another in equation form. Remember, up balances down, right balances left. Let's try with a hockey puck example. A hockey puck is sliding across the ice at a constant velocity. We always start with a force diagram. There's our hockey puck. Gravity's pulling down on it. It's on a surface, so that means that surface is pushing up with a normal force. And it says it's without friction. So we have no kinetic or static friction going against the motion of the object. And it doesn't say that it's being hit. It's just moving across the ice. This is after it's been hit. So horizontally, there are no forces. Ask yourself, vertically and horizontally, are these forces balanced? Well, horizontally, yes, they are balanced. If there's no force on either side, that's 0 newtons on the left, 0 newtons on the right, they're balanced, but they don't have names right now. The normal force and the gravitational force, my vertical forces, are balanced. Because they're balanced, we can write they're equal to each other. They're the same force. That puck is not accelerating upward, it's not accelerating downward. So normal force equals gravitational force. This force equation will help us when we need to infer unknown forces from known or calculated forces. In this example, a car is accelerating forward on a road. So it's on a surface and it's accelerating. It's going to be speeding up in this case. Always start with a force diagram. There's my car. Gravity's pulling down on it. It's on a road, so that's a surface. There's a normal force pushing up. The car has a kinetic friction force pulling back on it as the tire rubs against the road. Since forces come in pairs, as the tires push off the road, it's also applying a forward force. That's what's causing the car to move forward. This is Newton's third law. In this case, that applied force is applied much stronger or much more forcefully than the kinetic friction force. Since one is bigger than the other, these are unbalanced force. This is why we have acceleration. In this case, the car is speeding up forward. Even when we have unbalanced forces, some of the forces may be balanced. Horizontally, the kinetic friction force and the applied force are not balanced. One's bigger than the other. They have a net force that's bigger or smaller than 0. Vertically, however, the normal force and gravitational force are balanced. I know this because vertically, the car's not doing anything. It's not speeding up in an upward direction. It's not slowing down in a downward direction. It's only moving forward. So vertically, it's technically standing still. These are balanced forces. If I can prove that I have balanced forces, either vertically or horizontally, I can look at my up and down force in this case and state that they're equal. So the normal force equals the gravitational force. Even though the kinetic friction force and the applied force are labeled on my force diagram, because they're unbalanced, they don't get a formula. When we talk about quantitative force diagrams, we're talking about force diagrams that have direction arrows, labeled forces, and numeric magnitudes. So we need to know not just which direction the force is pointing, but how many newtons of force and which force or what's causing that force. Some of these forces can be calculated using certain formulas that we're going to review. Others might have to be inferred using force equations, or they may be given to you in the word problem in many cases. Here's an example of a force diagram. In this case, we would have calculated the gravitational force by multiplying the mass by 9.8. Because I know that vertically Fn and Fg are equal, if Fg equals 2.5, then Fn equals 2.5. Fa and Ff in this case do not look balanced. Ff is stronger or a higher force than the applied force going the opposite direction. These are unbalanced. In this case, I can't use a balanced force equation. When we talk about Newton's second law, we'll talk about the formula that will help us find that applied force, as well as the net force or the change in force between applied and friction forces. A couple of forces can be calculated using some common formulas. These are the same formulas that we talked about during balanced force equations. The gravitational force we can always calculate by multiplying 9.8 times the mass of the object. 9.8 represents Earth's gravitational force constant. If we were on, say, Mars or the Moon, we would have a different gravitational force constant instead of 9.8. Friction forces can also be calculated. Friction forces come in two categories, kinetic and static. Kinetic forces, or friction forces, are forces caused by things moving, so things rubbing against each other. Static kinetic forces are those forces that keep something in place, keeps them from sliding. Either friction force can be calculated by multiplying the mu times the normal force of the object. Mu is a variable that represents the coefficient of friction. The coefficient of friction defines the relationship of two materials as they slide or stick to one another through friction. The two different materials determine the coefficient of friction. For example, there's a different coefficient of friction for a dry tire against a dry asphalt surface versus a wet tire on a wet asphalt surface. The closer this value gets to 0, the more easily the two surfaces slide past each other. This would be something like ice. The higher or closer we get to 1, we might see the objects sticking to each other more. This would be like racing tires, or even Velcro would be at the higher end. Unlike Newton's first and third laws, Newton's second law is actually a formula. F sub net, or the net force, equals the mass of the object times the acceleration of the object. Net force is the change or difference between opposing forces on an object. When forces are balanced, this net force is 0. When forces are unbalanced, you take the bigger force minus the smaller force to find the net force. If we look at the unit of force, newtons, we see kilograms times meters per second squared. That's the real unit for a newton. If we look at the formula for the gravitational force, well, mass is kilograms, and 9.8 must be meters per second squared. So that means when we look at acceleration of objects when they fall on the planet Earth, 9.8 also represents the acceleration of all objects falling towards the Earth. This formula only applies to unbalanced forces. Unbalanced forces cause acceleration. So if an object is accelerating, it has a net force. Likewise, if a net force acts on an object, the object accelerates. Let's examine a couple of acceleration examples involving Newton's second law. Elevators are a great place to observe and apply Newton's second law. If you're accelerating upward, there must be unbalanced forces. If a man of 55 kilogram mass is accelerating upwards at a rate of 1.5 meters per second squared, what is his normal force? Now in this case, we would be looking at his normal force on the scale. A scale, or a normal scale, actually tells us our normal force, not our weight. As the elevator accelerates upward, we have to ask ourselves, which way is the elevator accelerating? It's going up. So the unbalanced forces, think about it like a tug of war. The winning force is going to be in the upward direction, the higher force. We always start with a force diagram. So here's the man. He has a mass of 55 kilograms. We should automatically know that that means 9.8 times 55 kilograms to get the gravitational force of the object, or the man in this case. He's standing on a surface, so there has to be a normal force. Now this normal force, because he's accelerating upward, has to be bigger than our gravitational force. The unbalanced forces are pulling stronger in this direction. That's what causes the acceleration. So I know it has to be bigger, but I don't know how much bigger. So I'm just going to label it as a normal force right now. To find out how much bigger or how much smaller an unbalanced force is, we need to calculate the net force, the change in force. This is the value that will either add on or subtract to unbalanced forces. So we bust out Newton's second law. Net force equals mass times acceleration. Well, I know the object's mass. The man's mass is 55 kilograms. His acceleration is 1.5 meters per second squared. That's positive acceleration. He's speeding up in a positive direction. Up and forward are always going to be positive directions. I multiply those together, I get 82.5 newtons. This is the net force. Keep in mind, this is not the normal force. This is just how much bigger the normal force is than my gravitational force. The net force is the change in force. At this point, it's always good to remind ourselves, which way is the elevator accelerating? In this case, it's accelerating upward. That's why I drew my normal force with a bigger arrow, a bigger magnitude. The gravitational force will never change. It's based on the relationship between our mass and the Earth's mass, or the object's mass and Earth's mass. So knowing which way, in this case, the bigger force is, I'll know where to add my net force. So I'll take my force equation. In this case, in order to create a balanced force equation, I had to add on the net force. So I have the normal force equal to the gravitational force plus the net force. This is a little twist on creating balanced force equations. Gravitational force is 539 newtons. The net force, or the change in force, is 82.5. I know that the normal force needs to be bigger. It needs to be unbalanced in that direction. So I'm going to add them up. 621.5 newtons. That's my normal force. I know I'm done when I have all of my forces labeled and a number, or a numeric magnitude, next to each label. Let's see what happens when the elevator goes down the elevator shaft. If you're accelerating downward, there must be unbalanced forces. So in this case, we have a 55 kilogram mass, or a man in this case, speeding up downwards at a rate of 1.5 meters per second squared. What is his normal force? So what is the force that the floor of the elevator is pushing up on him? Elevator problems are great because we've all ridden an elevator at some point. As that elevator speeds up towards the ground, you almost have that feeling like you're floating. So we have to think, which way is the elevator accelerating? It's accelerating downward. It's pushing down more than it's pushing up. That's why the elevator's floor feels like it almost falls out from under you. It's not pushing up as much as gravity is pulling down. These unbalanced forces cause acceleration. So here's our object. We have gravity pulling down. We already know that we take 55 times 9.8. Mass times 9.8 gives us our gravitational force. We've already determined that acceleration is happening downward. He's speeding up downward. So it's negative acceleration, but it's happening downward. That means my downward force has to be bigger than my upward force. Knowing which way the object's accelerating helps us figure out which unbalanced force is bigger, which unbalanced force is smaller. Since they're unbalanced, we know gravitational force, but we don't know the normal force. We need to figure out the change, or the difference, the net force between 539 newtons and the unknown normal force. To do this, we're going to use Newton's second law. Net force equals mass times acceleration. We'll plug in the mass, 55, and now be careful. I'm speeding up backwards. Down is backwards, so it's going to be a negative direction. That's a negative acceleration. It works like multiplication rules. A positive change in velocity times a negative change in displacement gives you negative acceleration. This is going to be very key to when we calculate our net force. Because when we multiply a positive 55 mass times a negative 1.5 acceleration, we end up with a net force of negative 82.5 newtons. At this point, I can try to create a balanced force, or a balanced force equation. Gravity could be balanced out if we take the normal force plus the net force. So in this case, we have to make a balanced force equation. So I'm going to plug in 539 for gravity plus that negative 82.5, that negative net force. That's going to give me a normal force of 456.5 newtons. This is reasonable because we already determined that the upward force, the normal force, should be smaller. This is why when an elevator speeds up towards the ground, it feels like the ground is falling out underneath you. Likewise, at this point, if you look down at that scale, it would look like you weigh less for that brief moment while you're accelerating. If you forget that acceleration in this case is negative, and you end up with a positive net force here, always look at whether the answer is reasonable. If you know that the upward force, or the normal force in this case, should be less, then know that you're going to be subtracting that net force. So if you didn't end up with a negative, subtract it so you end up with a smaller force up top. If you have a bigger force up top, a bigger normal force compared to your gravitational force, add that net force on. That's a positive change. Let's look at one more together. Keep some of these rules in mind about acceleration. If you're accelerating downward, there must be unbalanced forces. In this case, we're going to speed up downward. We're going to speed up a lot quicker than usual because the cable's going to snap. If the cable snaps, what is the normal force? What is the force that's pushing up on you? Or if you're standing on a scale like this gentleman is, what is the force that the scale reads? If the cable snaps, we need to look at the forces involved. Gravity is always involved. There's no way to get around it. So we have the same man, 55 kilograms. We multiply by 9.8 to get his gravitational force. If we're looking at the force diagram for the man who's moving in the elevator, gravity's affecting him, and when he was standing on a surface, he had a normal force. The real question here is, what caused the normal force in the elevator? The only thing causing the force from the surface was the fact that it was being held up by a cable. If there's no cable, there's no normal force. So what is our normal force? In this case, it's 0 newtons. When I draw a force diagram, I wouldn't even draw a normal force going straight up or perpendicular to my surface. So in this case, what is the elevator's acceleration? It's 9.8 meters per second squared. We determined that all objects, if you ignore air resistance, all objects accelerate towards the ground at the same rate, 9.8 meters per second squared. That's why if you drop a crumpled up piece of paper and a big heavy rock, they hit the ground at the exact same time. On your own, give this problem a try.